Hello, this video includes information on limiting reactants and percent yield calculations.
What we're going to start dealing with now are what are called limiting and excess reactants. And before we even start dealing with them with respect to chemistry, let's talk about more maybe everyday kind of things. So we're going to go back to that idea of recipes in a way and use that as our analogy. So let's say that we are going to make a sandwich, and it's a super simple sandwich. So it has 2 pieces of bread and 1 slice of cheese, and that equals our sandwich. Okay, so that's kind of like an equation for a chemical reaction. And let's say that we go into our pantry and we find that we've got 28 pieces of bread. And then we go into our refrigerator and we have 11 slices of cheese. Well, the 28 slices of bread can make 14 sandwiches. Again, the ratio is 2 slices of bread for every 1 sandwich. That's where this conversion factor comes from. We could probably do it in our heads, but the numbers will get harder. So we want to, kind of get the concept down of how to do it. And if we were to look at the slices of cheese, since we have 11 slices of cheese and it's a 1-to-1 ratio of cheese to sandwiches, we can make 11 sandwiches. Okay, well, we can make 14 sandwiches with our bread, but we can only make 11 sandwiches with our cheese. Okay, so what does that mean? Okay, well, it means that we're going to run out of cheese and we're going to have extra bread left over. Okay, there's no more cheese to make sandwiches with. We stop making sandwiches and we have bread left over. Easy enough concept. So when we talk about the substance that runs out, okay, that substance is called the limiting reactant. And the stuff that we have left over is called our excess reactant. Okay, those words are pretty easy. The limiting reactant limits the reaction because we run out of it. And the excess is the stuff we have left over. So let's look at this in terms of chemistry now, but it's the same general principle. So let's say that we've got hydrogen gas and we're going to react it with chlorine gas and we're going to produce hydrogen chloride gas, and it's balanced. We've got a 1-to-1-to-2 ratio, a lot like we had 2 slices of bread and 1 piece of cheese to make a sandwich. Same kind of idea. And let's say that in a container, we put 6 moles of hydrogen gas and we put 4 moles of chlorine gas, and we want to find out how much hydrogen chloride can we make. Well, we're going to use our balanced equation just like we did with our sandwiches. So 6 moles of hydrogen is going to enable us to make 12 moles of hydrogen chloride because it's a 1-to-2 ratio. But 4 moles of chlorine are only going to allow us to make 8 moles of hydrogen chloride because it's a 1-to-2 ratio. Well, we can't make 12 moles of hydrogen chloride because we stopped the reaction after we've made 8. So that means the chlorine is our limiting reactant. LR just stands for limiting reactant, so we don't have to write it out all the time. It's the limiting reactant because it runs out and it limits how much product we produce. And the value that we get with our limiting reactant is called our theoretical yield. It means that ideally, okay, in a lab, if we had 4 moles of chlorine and we reacted it with 6 moles of hydrogen, theoretically, we can produce 8 moles of hydrogen chloride. So if we look at this little picture over here, we end up with 1, 2, 3, 4, 5, 6, 7, 8 HCl molecules, and we have 2 hydrogen molecules that are left over. They have no chlorine to react with, so they're going to stay as H2 molecules. All right, so let's look at another example. This time, we have hydrogen gas reacting with oxygen gas to produce water. Okay, now the difference here is it's a 1 or 2 to 1 to 2 ratio. And it says determine the limiting reactants, the excess reactants, and the theoretical yield in grams for the above reaction if 4 grams of hydrogen and 8 grams of oxygen are reacted with each other. So we're going to start by doing 2 stoichiometry problems. We're going to go from 4 grams of hydrogen to grams of water and see what we get for an answer. And then we're going to go from 8 grams of oxygen to grams of water and see what we get for an answer, and then compare the answers to find out what our limiting reactant is. So we'll do the first one together, and then I'll let you do the second one. So when we look at the first one, we'll say 4 grams of hydrogen. Okay, well, the balanced equation is a mole ratio, so we're going to go from grams to moles in the first step. Again, this comes from the periodic table. Now that we're in moles of hydrogen, we can go from moles of hydrogen to moles of water. This mole ratio comes from the balanced equation. And then we're going to go from moles of water to grams of water. This comes off the periodic table. So if 4.0 grams of hydrogen reacts, we can produce 33 grams of water. Okay, so the same concept, I want you to take 8.0 grams of oxygen and figure out how many grams of water we can produce. Same idea, you're doing a stoichiometry problem. You're going from grams of oxygen to grams of water. So 8.0 grams of oxygen, we're going to go from grams of oxygen to moles of oxygen. Again, this is off the periodic table. The balanced equation tells us it's a 1 to 2 ratio. Again, we're going to put the 1 on the bottom because we want to cancel out oxygen. And we'll put the 2 on the top because we want to convert to water. And then we'll go from moles of water to grams of water using the periodic table. So if all of the hydrogen were to react, we could make 33 grams of water. If all of the oxygen were to react, we could produce 9 grams of water. So we can only produce 9 grams of water because we run out of oxygen. So oxygen is our limiting reactant. LR just stands for limiting reactant. So what's the, oh, this is a different thing. So the theoretical yield is 9.0 grams. I don't think I isolated that. So then it says, what is the mass of the excess reactant left over? All right, well, the excess reactant is the hydrogen gas. So what we want to do is use the limiting reactants to figure out how much hydrogen reacts. Okay, once the limiting reactant runs out, the hydrogen stops reacting. So we want to find out how much hydrogen reacts, subtract it from how much we have, and that'll tell us how much is left over. So it's another stoichiometry problem. So we have 8.0 grams of oxygen. We'll go from grams to moles. It's a 1 to 2 ratio to get to hydrogen. And then we'll use our periodic table. And this number, 1.0 grams, this is how much hydrogen reacts with the 8 grams of oxygen. Then the oxygen runs out. We can't make any more hydrogen. Now, the question didn't want to know how much hydrogen reacted. The question wanted to know how much is left over. We started with 4.0 grams. We decided that 1.0 grams reacted. That means the rest of it is in excess. So we just have to subtract the total mass that we started with from the mass that reacts, and that tells us the mass that's left over. All right, so let's try another one. calculate the mass of sulfur dioxide produced when 30.0 grams of carbon disulfide reacts with 35.0 grams of oxygen. And we want to identify the limiting reactant and calculate the mass of the excess left over. All right, well, here's the balanced equation. Okay, so sulfur or carbon disulfide is CS2. Oxygen is O2. Carbon dioxide is CO2. It actually doesn't even tell us in the problem that it's carbon dioxide. And sulfur dioxide is one of our products. All right, so we have 30.0 grams of carbon disulfide. Okay, so we want to find out how much sulfur dioxide can be produced. So there's our first stoichiometry problem. Then you're going to take 35.0 grams of oxygen and find out how much sulfur dioxide could be produced. There's your second stoichiometry problem. From that information, you can figure out what's your limiting reactant. Is it the carbon disulfide or is it the oxygen? And then once you figure out which is the limiting reactant, use it to figure out how much excess reacts. And then you can figure out how much of that excess is left over. Okay, so you have 3 different stoichiometry problems you have to do in order to answer this question. 35 grams of oxygen. We're going to go from grams of oxygen to moles of oxygen. This time the balanced equation is a 3:2 ratio. And then we're going from moles to grams of sulfur dioxide. So 46.7 grams of sulfur dioxide can be produced in that first step. And then for the second step, we're going to take the 30 grams of carbon disulfide. We're going to go from grams to moles. The balanced equation tells us it's a 1:2 ratio to get to sulfur dioxide. And then we'll go from moles of sulfur dioxide to grams of sulfur dioxide. So we get 50.5 grams of sulfur dioxide. Now, from there, we need to decide what our limiting reactant is. So we can produce 46.7 grams from our oxygen being consumed. And we can produce 50.5 grams from our carbon disulfide being produced. Well, we can only produce 46.7 grams because then we run out of our oxygen. So the oxygen is the limiting reactant. Okay, so now that we know oxygen is the limiting reactant, it limits how much carbon disulfide reacts. So we have a third stoichiometry problem we're going to do from 35.0 grams of oxygen to carbon disulfide. That'll tell us how much reacts. We want to figure out how much is left over. All right, so 35 grams of oxygen. We're going to go from grams of oxygen to moles of oxygen. We're going to go from moles of oxygen to moles of carbon disulfide. Then we're going to go from moles of carbon disulfide, there's an extra S in there, I think, to grams of carbon disulfide. So 27.8 grams of carbon disulfide can react. We had 30 grams. Only 27.8 grams reacted, and then the oxygen ran out. So the difference between those two numbers tells us how much is left over. It's just doing a little bit more with a basic stoichiometry problem. So hopefully as we just build on it, we're doing okay. All right. So we're going to talk about what's called percent yield. And when we deal with percent yield, okay, it is the theoretical value, okay, is what we calculate compared to the actual value, which is what we get in our lab. And to calculate percent yield, we take the actual value, okay, which is the measured value that we get in our lab, divide it by the theoretical value. That's the calculated value or the right answer or what we get from our stoichiometry problem. And we're going to multiply it by 100. Okay, now think about this. Let's say that we were to do a lab and the theoretical yield was 50 grams. And we do the lab and we produce 50 grams. Okay, well, 50 divided by 50, that's 1, times 100, that gives us 100% yield. Okay, we got 100% of what we expected to get. If our actual value is less than our theoretical value, the farther away from the theoretical value we get, the smaller the percent yield is. So we'll look at a couple of questions that go along with that. So for this practice problem, okay, it says, upon reaction of 1.274 grams of copper sulfate with excess zinc metal, 0.392 grams of copper metal was obtained in this reaction. Okay, so here's our reaction. Okay, we've got copper sulfate reacting with zinc to produce copper and zinc sulfate. Okay, now we're given the amount of copper sulfate, so we're given this number. It says we have excess zinc. The only reason it says that is because then we know that all of this copper sulfate reacts. So what we would do first is figure out the theoretical yield. Okay, we'll do a stoichiometry problem. We'll take the copper sulfate and do our stoichiometry to figure out how much copper we should produce. Okay, that's our theoretical yield. Then we would take the value that we got in lab, okay, that's the 0.392, divide it by the theoretical or the calculated value and figure out what our percent yield is. So the first thing we're going to do is just a stoichiometry problem. Okay, here's our reaction. If we have 1.274 grams of copper sulfate, figure out how many grams of copper we should produce. What's the theoretical yield? And since the equation's already balanced, it's a 1-to-1 ratio. We still want to show it in our stoichiometry. Maybe the math is a slight bit easier. So convert grams of copper sulfate to moles to your 1-to-1 ratio to your moles to grams. All right, so if we did the theoretical correctly, we've got 1.274 grams of copper sulfate. We're going to go from grams to moles. The balance equation is a 1-to-1 ratio. We're going from moles to grams. So we should produce 0.507 grams of copper. Okay, well, in the lab, we didn't produce 0.507 grams. We produced something less than that. We want to figure out our percent yield. Okay, so to figure out the percent yield, we would take the actual value, which is what we're given in the lab, divide it by the theoretical value, that's what we calculated in the stoichiometry, and multiply it by 100. So 77.3%. Excellent. So let's do another problem. Okay, what is the limiting reactant? Oh, you know what? I don't want to do that. Never mind. No, we do want to do that. Okay. So this is just adding on to it. We have a reaction. Okay. We have 0.200 moles of P4 and we have 0.200 moles of oxygen. Okay. So the first thing we want to do is figure out what the limiting reactant is. Okay. It's moles. So we're good with that. We do want to go to grams of P4O10 because we're going to be using that later on in our percent yield calculation. So go from moles of P4 to grams of P4O10 and go from moles of oxygen to grams of P4O10 and figure out what the limiting reactant is. You don't need to figure out how much excess there is. This question isn't going to ask that. Okay, so I'm getting 56.8 grams from the 0.200 moles of P4 and 11.4 grams of tetraphosphorus decoxide from the 0.200 moles of oxygen. All right, so here's the next part of the question. Calculate the percent yield if 10.0 grams of P4O10 is isolated in a reaction. So when we look at this, this is how much product we should produce, okay? Because the oxygens are limiting reactant. So this is our theoretical yield. This is our experimental yield. What's the percent error or percent yield? Sorry. Okay, so we take the actual value, 10.0, divided by the theoretical value, which is the 11.4, and multiply it by 100. So we got 88% yield. Not bad.